So first things first, a couple orders of business. There's no class on Tuesday, election day, go vote or help the country, or if you're not in America, just kind of cross your fingers and hope that we don't screw this up. That's number one. Number two, I'm probably going to end class a few minutes early today. My son has a class presentation on Zoom that I want to get home for, so I'm going to rush out of here and do that. I'm assuming, based on the sheer volume of submitted homework assignments that I received between 3 a.m. and 5 a.m., that this was a harder homework than other ones. Either that or you're all very busy and you don't really like sleeping. Either way, that's okay. But I hope today we can go through these things. There's a lot, so feel free to kind of go through, if you're volunteering to walk through a problem, to go through kind of quickly, and people can stop and ask questions along the way. But I guess in general, any comments or questions or remarks about the homework? Like how was this thing overall? Or let me put it a different way. How do you feel about these using these perturbation methods now that you've spent some time actually hands-on doing them on your own? Kind of separate from like the homework as an assignment.
I think the homework definitely helped a lot to sort of conceptualize and put it into practice.
That's good to hear. Okay, cool.
I think conceptually a lot of the concepts aren't that hard. It's like what kept tripping me up was trying to remember what variable was which in Mathematica, and like all the different expansions we had and which one was your guess and which one was you just trimming it down and things like that. So there's a lot of like moving parts that was just a little hard to keep track of.
Yeah, that makes sense. I think that's fair. I will remind you all that, like, this will be both the first and probably last time you'll ever have to do like 5 completely unrelated problems that use these techniques. And so a lot of the confusion, kind of will go away by design, because you'll be working on one problem that you'll probably kind of spell out everything with the same level of detail and kind of like tediousness that you kind of did for all of this. And so it can help for some of those things. Like I think homeworks like this are weird because there's almost so much to keep track of that it can be really daunting. But this is not typical. Like this is not the way you'll encounter this stuff in practice. So I don't know, hopefully that helps. Should we just jump into it? What do you think? Any other things? Oh, there's a couple comments. Hold on. Yeah, for sure. Yeah, I think that's a great comment. So there's a remark in the chat about the Mathematica slowing you down and writing it out helping. And I think that's a really good remark. I probably should have encouraged you all to do more of that. One of the things I was trying to accomplish with kind of doing a lot of this stuff in Mathematica is for each person in the class, there are going to be some things that are obvious and some things that are really you're not comfortable doing. And for some that might be doing Taylor series expansions. For some that might be doing integrating a simple ODE like y prime equals y naught. For some of them it might be algebraically simplifying an equation and feeling comfortable knocking out terms of higher orders and epsilon and whatnot. And so I think probably to the detriment and probably the confusion of some, I was trying to show how you can do all these things in Mathematica. My hope, I think in reality, what you'll find yourself doing is kind of, at least until you maybe get more comfortable in the software program, is kind of doing things out by hand, getting to the point where you're like, I need to figure out what this is, going to Mathematica, using that tool to move you forward, and then going back and doing things. That's how I used it for a while. Now I'm at the point where I kind of use it like truly as a notebook, because I forget what I was doing and I lose stuff. And if I have it all laid out as clear as possible, it's actually on a computer file. It's helpful to me. But I should probably say that Like Leah, that's a smart remark, and I probably should have encouraged more of you to like kind of do these things on pen and paper and use Mathematica as a tool to help you kind of pass the hurdles that you encounter. But yeah, thank you. All right, the first problem had two components. So we can kind of split it up here, and they're both polynomials. So we can have, if someone wants to do one of them, we can have someone else jump in to do the other. Any volunteers?
Start if you want.
Sure. Is that Jacob? Or who was that actually? Sorry.
Yeah, me.
I'll make you co-host. I don't know if I can make everyone co-host. Okay, excellent. All right.
Split up, and I'll go ahead and share. All right, can you guys see the screen and hear me?
Yep.
Yes.
So yeah, problem one was just a polynomial. So I went ahead and made a function for that polynomial that took in x and epsilon. So it just looks like this. And then the first part was just getting the analytical solution and plotting that to sort of have like a benchmark curve, like we've been doing in the problems in class. So next, something we have to do in Mathematica is make our guess. And to do that, it's just this sum function, taking in whichever variable our variable of interest, and then n. So then here, I'm just testing out the guess. And now, so we're going to move on to order 1, or epsilon to the 0. So you can plug in your guess directly to the function, and you get this. I think it's also important to note that in this original function, there's only one variable. It's not like x as a function of something else. So you're able to plug in your guess directly to the function. But like in some later problems where you have like x as a function of t or y as a function of x, for example, when you take epsilon up to higher orders, then you have to go through some extra steps. You can't just plug this in directly, but that doesn't really matter here. So anyway, we plug in our guess. We basically cut out all the higher order terms because we're just taking it up to order 1. And then we solve for x naught. So we get two solutions. And technically you have to plug it back into your guess, but your guess is just x naught. So these are the two solutions, and we plot them. And we see that against our benchmark curves, they do a really bad job. So we have to take it up to higher orders. So now we're going to go up to order epsilon, and it's really just the same process. So I'll start to go quicker here. So yeah, you plug in your guess. You cut out to all the terms of up to epsilon, and then so you solve, and you plug back into your guess, and then you can plot, and we do a little bit better now. So these are the original two curves, the flat lines, and these curves do a little bit better because they have a non-zero slope. But we can do better. So I ended up just taking it up to order epsilon squared, and I'll just skip through this at this point because we've gone through this process. And you end up getting these curved curves. that do a lot better. So they go probably up to like here, epsilon of like 1.5 here. Yeah, so like 1.5 is pretty adequate. So this is where I stopped.
All right, thanks. Any questions? Anyone approach it differently or get some or have anything to add? I would say just in general, you're right that the order zeros approximation doesn't do particularly well. However, we should not be too hard on it. It does capture the values at exactly epsilon is equal to 0, which could be worthwhile. The second remark I would be is that, remember that epsilon is a small parameter. And so once you get around order 1, like that's a pretty big value. So generally plotting these things from kind of 0 to 1 is a good way to test your estimate, because once you're getting around order, epsilon is around 5 or getting closer to 10, like it's really quite a large parameter.
That's a good point.
Which might mean, like, especially for the differential equations, which might mean you kind of actually have a different parameter in your problem that's smaller. And so it might, I guess the broader remark is like, if you're dealing with something that's like epsilon is to the, a number like 5, you should kind of look at your problem again and make sure there's not some other small parameter that you're missing. Because that's a large number, especially in problems with differential equations. Cool.
I have a question.
Yeah.
So I haven't thought about this because I always think about epsilon as between 0 and 1.
Mm-hmm.
Is the epsilon goes to negative always valid?
Yeah,
yeah.
It's so I guess there's not like formal bounds on epsilon. Epsilon is generally is taken to be a positive number roughly between 0 and 1, and typically the quote unquote negative of that value is dictated by the sign on the term that epsilon appears in. So if it's like x squared minus 2 epsilon, it's almost gonna, if epsilon's negative, it's gonna kind of change the form of your equation, which is important to know about, because that'll change like the types of ways to evaluate the stability of that equation or whatnot. So typically epsilon is, you're gonna see people talking about it kind of from 0 to 1, not necessarily bound at 1, but oftentimes if the parameter is actually negative, usually you think of it as like the term in the equation is negative, but epsilon is positive, if that makes any sense. Now, if you have a problem in which there's a sign change in epsilon, like then you're kind of looking at almost like 2 different problems, one in which the term in your equation is positive and one in which the term in your equation is negative. But I would say the way you were interpreting it is kind of how I interpret it as well, which is like typically treating epsilon as some value, between 0 and 1, and oftentimes between like 0 and 0.1. But I think that's how I think of it, at least. That's a good question. Thank you.
Thanks for the answer.
Can you go back to your analytical solution for order epsilon?
So the question is, can you scroll up to the analytical solution? So you mean analytical solution or the order epsilon solution?
No, like the order epsilon solution.
Yeah, scroll down to the order epsilon solution. Yeah.
Not the plot, but what the values were for.
Yeah, so it's 1/2 times -1 plus or minus √5. Which certainly seems to intersect the analytical solutions when epsilon is equal to 0.
Did you get something else?
Yeah, but I'm not confident in it.
He said yes, but he's not confident in his solution. So
I had the same thing, just with the +2 epsilon.
Yeah, I have it.
2 epsilon?
Yeah, so it's 1/2 times -1 plus -5, same as that, but then plus 2 epsilon.
Well, this solution should be at order epsilon to the 0, so the epsilon should,
Oh,
I would imagine you
no,
probably got
this
that.
is Order epsilon to what?
No, this is order epsilon to the 0.
Oh, so I was wondering what the order.
Oh, sorry, so can you scroll down one more? To order epsilon to the 1?
Yeah.
Oh,
Yeah, there you go. There's the solution that you all have. Perfect. Excellent. All right, thanks, Jacob. Does anyone want to do part B of this?
I can do it.
Go for it.
Excellent. Who said that? I can't see.
It's Aaron.
Cool. I think you are now co-host.
Everyone see it?
Yep.
So I started off with the approximate solution, this power series expansion. Over here, I did the general expansion. I just used the same formula as before, using the notation and symbolizing, and then I inputted the solution. Inputted the equation for the solution, which is epsilon x cubed minus x minus 1. And as with most of the problems, I started out with an analytical solution. So I just did a solve, and oh, 1 second, sorry. Sorry, my screen is glitching. Is it working now? Can people see?
I can see it, yeah.
Okay, yeah, so if you can see the analytical solution, there's a fairly complex curve over here. So that probably means we're going to have to do a singular perturbation, but before that, I start off with a regular perturbation. So first, I make the expansion general for the 0th order, so I put expansion general 0. And then I take a series of that to make sure that basically, if I don't do this, it's gonna, my kernel has run again, but basically I need to do that. So I get the exact epsilon 0 solution, and I get x naught equals 1. And then for the approximate solution for the order epsilon, I pretty much do the same.
No. I think you might have frozen.
So that we solve, and then we can solve for x1 and get x1 equals -1. And so you can connect, you can combine these two to get your sort of your regular perturbation up till order epsilon. And so I just plot that, and I plot that next to the curve, and I see that it's variable change where I express a new variable x in the form of a new uppercase variable x in the form of x and epsilon to the power divided by epsilon to the power of gamma. And then I define the new equation basically with my new epsilon gammas. So because this variable was x, it now becomes x equals uppercase x, epsilon to the gamma, and then the x cubed becomes times epsilon 3 to gamma. And then I do a dominant balance, which this is my equation that I need to make sure becomes larger as epsilon goes towards 0. So I balance the first and the third terms, which is the exponent, the power of -1, which is 0, and then the exponent of epsilon 1 plus 3 gamma. Then I can get gamma equals -1/3. And I plug that gamma back into my equation. And as I noticed that as the gamma term, as my epsilon term gets small, this significant x cubed term sort of just doesn't get larger. So I need to do another balance. And for this one, I noticed that I get gamma equals -½ and this actually is the result we want, because as epsilon goes to 0, the x cubed term gets very large. So then I do an approximate singular solution, basically just like we did for the regular solution. I just made another expansion that symbolizes stuff in uppercase X, but apart from that, I basically take it up to the 0th order. And then I used the same thing we did in the most recent class notes, the Mathematica Notebook 7, and basically I solved for x naught, and I noticed that I have three values of x naught, uppercase x naught, and basically what I do after that is I need to convert it back to the original variables, which is lowercase x, and divided by epsilon to the gamma. Gamma in this case is -½ and so I get these three solutions: -1 over square root of epsilon, 0, and 1 over square root of epsilon. And when I plot this, it looks very similar to the analytical solution. And then I decide to go up another order to order epsilon. Basically, I do the same expansion general, and then simplify it up to the first order of epsilon. And then I solve for x1, but before that, I make sure to sort of plug in the values, the solutions I got for x naught. And so I got 1 over 2 square root of epsilon, -1 over square root of epsilon, and 1 over 2 square root of epsilon. I need to convert that, I need to put that back into the equation and also convert it back into x variables. And once I do that, it looks like this, which is closer than what it was before. Yeah.
Excellent, thank you. Are there questions?
I have a question on that one. I got like the same answer that was just shown, but when I was going through this, I kept all of my solutions from the singular perturbation. So I ended up having like 3 solutions from the singular perturbation, one of which was -1, which I think was your order 1 regular perturbation solution. So I guess I'm just wondering, if you have a singular perturbation problem, do you actually need to do the regular perturbation first? Or if you keep all of the solutions from your singular perturbation, will you get the solution that is your regular perturbation and then the singular perturbation solution? I was just going through and I kind of felt like doing the regular perturbation didn't help me at all because I ended up getting that solution anyway.
Yeah, I think we encountered this before when we first introduced the singular perturbation, kind of talking about how you end up seeming like you have more solutions, but you end up kind of recovering the same solutions you had before. I think that's generally true for polynomial expressions. And what I can't remember is if that's true for perturbing initial value and boundary value problems, is if you recover the regular, kind of the outer solution if you're looking in the inner solution. And my sense is that you don't, but I should probably kind of double check, or maybe we can kind of keep that in the back of our mind as we're going through these rest of the problems to see. I would speculate to say I think that's true certainly for these polynomial expressions, and I want to double check on if it's true in general. So it's kind of a half answer.
Okay, that makes sense. Thank you.
Yeah, question in here.
I missed what the final equation was. Did it come out as some long, complicated expression?
Aaron, would you mind sharing your screen again just to show what the final expression was?
Sure, I can do that. Share screen. 1B. So the final expression was, oh, that's the wrong one, sorry. That's 1A. 1 second. Yeah, the final expression was this over here. Oh, why is it not? Sorry, it's not opening. I can just close my Mathematica and open it again. Yeah, that should work. So the final expression would be yeah, it's this one. Well, any one of these three are, there's three different solutions, so there's three expressions. -1, 1 plus square root of epsilon over 2, and then 2 plus square root of epsilon, 2 square root of epsilon.
Yeah, and I feel like I mean, don't we actually learn something from the regular perturbation? Because you've taken this now out to order epsilon. Is this like a 2-term? Or I guess you're at order epsilon here. Yet the regular perturbation is still to order 1, right? Sorry, the third solution, I should say, is still to order 1 here, right?
Yeah.
Whereas,
Actually, I think I took it to order epsilon, but I took it to order epsilon. Yeah.
yeah, so up here it's, your solution is -1 minus epsilon. But if you scroll down, I think unless you didn't substitute in, I think you end up with -1.
Right. Yeah.
I feel like we lost something, I guess, without doing that. Like almost like we would have to take this to a higher order, unless something's missing here, but I don't see it.
Yeah.
Unless I'm missing something, it seems like we might have actually gotten a little bit more information from the regular perturbation than we had from just this singular perturbation.
Yeah, to get the actually the question is asking to find a 2-term asymptotic expansion, but if you only use the singular perturbation, the one of the solution that has x naught as 0, so you end up having just -1 in your solution. You actually have to go 2 steps further to find the second term.
Yeah.
If you're using singular perturbation. So it's easier to do it on the regular perturbation side for that solution.
Yeah.
Oh, so I could have gone higher on the regular perturbation to that.
No, I guess what we were addressing was that question of kind of like, do you need to do the regular perturbation? And here, by taking only the singular perturbation out to order epsilon, you actually only get an answer of -1 for that other root. Whereas when you took the regular perturbation out to order epsilon, you got something of like -1 minus epsilon. So you kind of had a better approximation for the third solution, I guess,
Right. Yeah.
by doing the regular perturbation.
Yeah, that makes sense.
Yeah, question in here?
I mean, just kind of, basically it's saying that the order epsilon squared of the singular perturbation would be the same as the order epsilon regular perturbation.
That's what it's looking like. I
Yeah.
want to. I don't know if that's true in general, unless yeah, but that's what it's looking like at least here. Yeah.
I think that's true, but yeah, it might not be super general.
Yeah, I'd want to confirm that it's true in general, but yeah, I think at least that's what we're seeing here.
Okay.
Yeah.
So I have a quick question on that.
Leah.
So I only did the singular perturbation because like I had seen in like past problems with polynomials that it gave us like the same. I thought it gave us the same thing, so I didn't do the regular part. So since we're seeing this right now, how would we know when we did the regular perturbation and then went on to introduce 1? How would we know like which roots to keep from which one? Does that make sense?
I guess I'm kind of confused, because if you're doing the regular perturbation, there's only one solution. And so you don't really have a choice of what to keep. And if you're doing the singular perturbation, it's kind of showing you all three of these roots. And now what I don't know is, like, are you guaranteed to get 3 real roots, you know, like, as you did here, where we had 3 solutions that are all real, whereas clearly this problem has a kind of a bifurcation. As you start from like epsilon of -1, you see there's only one real solution, and then you get to around epsilon of 0.0001 or something, and you see that there's the emergence of like 3 solutions that are real. And then as you go further to the right, you lose one of them, and then eventually you lose and only have 1 real solution. So what I don't know is, like, if in general trying to do the singular solution will kind of always give you that 3rd solution to the same order of your approximation as you would have gotten had you done the regular perturbation. So it's not really a great answer to your question, but like, if you're doing the regular perturbation, you're guaranteed to kind of find one of the roots when basically for the case in which the high order polynomial term in your expression is not important, when it is actually small. And then what I'm not sure about, and I'm not as confident about, is kind of knowing if you'll kind of be guaranteed to have all 3 of these solutions, or in the case of a higher order polynomial, if you'll always have kind of the real solutions or imaginary ones kind of over the domain that you're interested in. So in general, my experience with this is people don't typically just skip right to the singular perturbation. It's more, I usually see this approached by people doing the regular perturbation for one region and the singular perturbation for the other, and then oftentimes kind of matching those together. But like I said, maybe that's just, yeah, I don't have a good reason for why. Yeah.
Okay, thank you.
All right. What is problem 2? Which one's that? And is anyone interested in going through problem 2?
I can go through it.
Ah, thank you. Who said that?
Susan.
Let's see. Sorry, did I enable screen sharing?
Professor, I think you chose the wrong person.
Oh, sorry. Okay.
Yeah.
Who can you? Sorry, it's. I would think it's easier, but I can't actually. Sorry. Who's going to present?
Susan Elliott.
Ah, Susan. Sorry.
All good.
Susan.
Okay.
Is that,
I
I can leave.
yeah, this one.
Yes, that's fine. Okay, cool.
Okay, so you should be able to see the screen. So this was the problem 2 projectile with air resistance. I just started with defining the problem as everyone else does. Looking at this one, it's always going to be a second order differential equation, even like this epsilon doesn't change that fact. So it's just going to be a regular perturbation problem because it's not changing the order of the differential equation. So I've defined my problem, and then I go and I solve analytically or numerically. So I wasn't able to analytically solve this. So this was a numerical solver, but same concept. We're trying to get something that we can compare it to. So we end up with this curve, which just to check kind of makes sense because it starts as an upward velocity. So your displacement is not going to be negative until it's kind of reached that peak and come back down. So the numerical solution makes sense conceptually. So then we define our guess. It's the same guess as everyone has been using. Just now the variable inside it is t as opposed to x. And that's important because it's a differential equation. So we need to know that that variable is not just a variable in and of itself, but is a variable dependent on something else. So then the first thing to do is the approximate solution. And we start by plugging our guess into our original equation. And you also need to rearrange your boundary conditions because now we have those to solve these differential equations. But they were, I realize the statement is incorrect. I had originally put my boundary conditions both at 0. So they don't actually remain as they are, but you can see here that my boundary condition is correct. I just wrote the wrong words. You have an upward velocity of 1. So now we're going to take that this differential equation up here and output 92, and we're going to expand it about epsilon equals 0 using a Taylor series. And then we get a much simpler differential equation. This is just the order 1, so there's no epsilon. So we solve this differential equation. That's now our x naught, and we plug it back into our solution. Then plotting that versus the analytical solution or the numerical solution, sorry. You can see for this equation, it works up to like t equals 3, t equals 3.5. But we're going to take it out to order of epsilon just to get a more accurate solution.
Can I interrupt just for a second? So
Yep.
This is a problem that we have some physical intuition for, and I think it's good to stop and pause and check ourselves on what it's implying. So what is, and this is a question just to anyone, so what is the order epsilon, order 1 solution for this problem? Like, what's the physical meaning of that?
I guess that's without the air resistance.
So yeah, so is it without the air resistance? So
Well, it also just sort of undershoots the like where it hits the ground again.
yeah, so I feel like the term that introduces the air resistance is the first derivative of x term, right? And so our epsilon is actually multiplying the term in the denominator. So is epsilon in this problem a small parameter of kind of about, say, drag force to gravitational force, or is it something like initial velocity or like initial acceleration to Earth's acceleration? So like the non-uniform gravitational field problem.
I don't remember completely, but I think it looks, the epsilon looks similar to, there was like a G over R, or
Yeah.
I did deal with the Earth's radius and something else.
Exactly. So yeah, so the epsilon here is still about the small parameter being related to kind of the acceleration of the projectile versus Earth's gravitational acceleration. And so the reason why I'm asking this is because I want people to kind of be checking if the physics of the problem matches up what they expect. And so you kind of know how the so like if I was doing this problem as a research problem, I would probably first solve the basic analytical expression of x double prime is equal to -1, which would be no air resistance, no non-uniform, no non-linearity due to gravity. And then I would kind of add in the non-linearity due to gravity, and then I would add in the air resistance. And so we've talked a lot about what happens as the projectile enters a non-uniform gravitational field in which it'll go farther, it'll stay up in the air longer. But what are people's intuitions for what's going to happen if there's drag, if there's air resistance in the problem? Should the projectile stay up longer or shorter?
It should stay up longer because the drags keep like acting upwards.
Yeah, so we have two conflicting remarks. So in the class here, someone said it should stay shorter, and on our remote, the question is it should stay up longer. It's a tricky conceptual one, no?
Depends on the conditions.
It depends is a third option. I like that. That's a very scientific response. Well, what does your data show? Like, what does the numerics versus the analytical, versus the order one solution tell us? So this doesn't really matter, and so this is not me being too much of a stickler, but once x crosses 0, that's the projectile going into the Earth's surface. So kind of anything above 2 doesn't really, I guess it would make sense if you were like throwing a projectile up and then you were like off a cliff, I guess, and then it would kind of continue falling. But here it looks like when you neglect the gravitational field, that the projectile goes up higher and stays up longer. I think it'd be interesting if it were me. I think like if this was a research problem, not a homework problem, I would also want to compare this with the simplest possible problem, the analytical solution for the uniform gravitational field and no air resistance, to see if the projectile stays up longer or shorter in that case. All of this is not important for the homework. This is just the habit I want you to kind of get yourself into when you're developing models, and just trying to bring yourself back to like, what do you know? What is your personal ground truth? Like, what are you comfortable saying? Like, I understand how a projectile should work in the absence of complex gravity stuff and air resistance. And now I'm going to add physics onto that. And I want you to be in the habit of kind of pulling yourself back to the stuff that you're confident in, and then kind of stepping forward from there. So that's all. I just wanted to bring this up as a kind of important process for you to go through as you're modeling. It can help you catch mistakes. There's not a mistake here. I'm just bringing this up to say, like, this approach of kind of what are you confident in, and how can you check to make sure what you just did makes sense, is kind of a crucial process in the model development step. So anyway, I digress, and I just wanted to bring that up. But please continue. This is looking good.
I guess then from that, if it only matters out to t equals 2, the solution is more accurate. I guess I was kind of visualizing it as it was kind of falling off a cliff, which is why I was like, oh, it can go below 0.
Yeah, that's totally fine. Yeah, absolutely.
But yeah, so I guess whether or not you want the next solution, other than the fact that I think the homework says to take it out to 2.
No, I do. Please, yeah, please go on. Yeah.
Would depend on what you're looking at. But since like I'm assuming that you can go out farther, you would want to be able to possibly model farther than just the like 3.5 seconds or whatever it was that it was fine for. So then you follow the same process for order epsilon, where you just plug your guess in, and now we have our x naught, so we also plug our x naught in, and now we do have to change our boundary conditions. So it was 0 and 1, and now because we've already kind of used the 0 and 1 in the order 1, this actually becomes 0 and 0. Just based on how Mathematica has it, it will still look at x naught or x prime of 1 or x1 prime is 0, but it just looks weird. Within the same process, you expand that equation, because that equation can't be solved using the desolve equation, because it's just based on how the differential equation is. So we make out a normal or a series expansion, and then we solve it using desolve. So now that we have x1, we plug it back into our equation, our initial guess of x naught plus epsilon x1, and we get our order epsilon solution and plotting it versus both the numerical and the original guess, you can see it gets a lot closer at some point, because once again, overshoots, but yeah, so it works, as I commented, it worked well out to t around 4 when epsilon was 0.1, but then again, if you look at the height of the projectile versus the radius of the Earth, it might be a lot smaller. But if you're looking at that kind of epsilon, you could take it out even further, but I left it there.
Excellent. I think that was really good. That was really clear. Are there questions? Thank you. That was really nice. All right. We're moving on.
Yeah.
Reese, you said you wanted to do number 3?
I'll do the third one.
All right. Excellent. I'll mute over here. Do you want to just do your screen?
I was about to say, I wonder. Yeah, we can try that again.
However you want to.
Why don't you try muting and we'll see if there's a
Can you mute and turn your speaker off?
Yeah, I will do that. So I'm going to make you co-host. I'm going to mute.
All right. Any weird echoes? Hopefully not.
You can turn that they can hear you.
Yeah, can you guys hear me okay?
Yeah.
Okay, so you guys will listen through. Is that okay? You guys can hear?
Yeah.
Okay. All right. Let's share this guy. So yeah, essentially this is the nonlinear boundary value problem in elasticity. And so essentially we define our governing equations to start. I just used the derivative thing in Mathematica rather than actually doing that out. And then essentially, we weren't able to find an analytical solution. So I just used a numerical solution, and I just picked epsilon to be 0.1, but maybe you guys picked a different one. And then we also define the guess of our solution. This is all standard stuff. And then I kind of like this approach where I immediately kind of expand both the governing equation and the initial conditions. And then I'll just reduce those according to however far out I want to take my approximation. And so then just jumping right into the regular perturbation, going back quickly to the governing equation, basically we see that this y double prime term does not have an epsilon attached to it. And so therefore, I know that we won't have to do some sort of singular perturbation.
Can I jump in really quickly?
Sure.
This is a subtle one. So if you scroll up to your equation again,
Yep.
It's a subtle one because in one of the terms, the epsilon is multiplying a second derivative term. And so it could be a little confusing. That middle term that you have 2 epsilon y prime squared y double prime. It looks like when epsilon goes to 0, the y double prime disappears. But you clearly see when you're looking at the third term that you actually still retain a second order derivative in y, which exactly what you said is right. This will only require a regular perturbation. However, it's easy to get kind of tripped up here if you're kind of looking at it quickly. And if you're kind of curious of like, oh, here's an example in which the y double prime appears twice. Is this singular or not? Because the epsilon is multiplying it. It's not, because when epsilon is 0, you still have the ability to plug in your 2 boundary conditions when solving for the kind of order 1 solution. So what you said is correct. I just wanted to emphasize that in case there was any ambiguity for folks.
Absolutely. Yep. All right. So going to my approximate solution for order 1. Basically, I just took my expanded equations and then took a Taylor series expansion about epsilon, order 1. And then I was able to use dsolve and find a approximate solution for order 1. And then I can plot that approximate solution compared to my numerical one. And, I obviously had to plug in this same or I didn't have to in this case, never mind. And it looks like, mostly we're able to meet the numerical solution pretty well near the boundaries. But in between, it's not as great. There's a little gap in between the blue line, our approximate solution, and the red line, the numerical solution. And then I went to order epsilon, and kind of the same stuff everyone's talked about, but basically plugging in what we got for y0, and then doing the Taylor series expansion about epsilon to the power of 1 now. And basically we get our new governing equations and initial conditions. And again, Mathematica does this a little bit weird. Susan brought this up, but basically you'll see that these are actually equal to 0. They just keep like a 1 and a 1 on each side. Not a big deal, but anyway, something to bring up if it's confusing. And then basically we were able to solve this out for our y1. And then finally, we just plug in what we got for our y0 and our y1 back into our guess, and then plot our final solution for that. Hopefully you guys can see the yellow line basically lies right on top of the red line. Maybe I could have picked a different color. But yeah, now with our order epsilon approximation, we are now better able to capture the numerical solution in basically the center region of this plot. We're still able to get it if the boundary conditions are, but now in the middle we can capture it too. And yeah, that was it basically. Yeah, kind of the same. Sure.
Is this code live? Like if you run line 24, will it spit out those things?
Yeah, I just ran it.
Can you for the second line, or can you at the end of the second line add / capital FULL
full simplify?
Yeah. And that gets rid of the problem that you and Susan both had.
Yeah.
With the confusing kind of 1 plus 1. So it doesn't kind of automatically simplify it for you unless you tell it to. And you'll notice that it probably still didn't full simplify it the way you and I would full simplify it all of
Get
us.
rid of the epsilon.
Because it's not going to make any assumptions about epsilon. And so if you tell it that epsilon's not 0, then it'll simplify it even further. But this is kind of why that those terms remain, because it essentially will just kind of term by term evaluate the expression, and then only look for like ways to rearrange and simplify the equation if you tell it to. So that's why this should resolve that confusing thing that you all found. So. All right, questions about this one?
Go back to the plot.
I think this was a boundary value problem. Is that correct? Like we had two boundary conditions.
Yeah.
And so you should know, and I think you said this, like, oh, look, it matches the boundary conditions well. It has to, like, you forced it to.
Yeah.
And so for a boundary value problem, it's always going to be away from the boundaries that things go awry. And so it's always going to be kind of how is it getting you between those two boundaries, and how well is that approximation working inside there? Because you're kind of forcing it, even at order 1, to match the boundary conditions, which eventually, as we get to more complicated problems, makes things harder. That's what makes boundary values problems harder than initial value problems, that it has to match the boundary conditions kind of at both ends, at whatever ends in your domain they exist at, even at order 1. So these problems are, in general, always harder than initial value problems for a variety of reasons, including existence of solutions, uniqueness of solutions, and so on and so forth. So, were there any questions on this? Did anyone do it differently, or?
I have a question. So, what's the difference between the simplify and the full simplify? Because so sometimes I use a simplify and it can meet my need, and sometimes full simplify can meet.
You can dig into the help file to find out the exact difference. My understanding is simplify generally uses less identities, and so therefore it's quicker. And so it will not use, I'm pretty sure it won't use like trig identities or ways to kind of connect
sines and cosines to exponentials. It might not use some of the more complicated like integral relations that Mathematica knows about. And so you're kind of trading speed in simplifying your expression, which like for complicated expressions, full simplify can take a really long time. I've had some that take like literally hours. And simplify is much quicker, but it comes with kind of possibly not simplifying the expression to the way that you would expect, because it might not use all the identities to simplify it. And so you can kind of dig into the help to figure out what ones it does or doesn't use. But yeah, I almost always use full simplify unless it looks like it's going to take a long time. And then I abort and go back to simplify.
Yeah, sure. Thank you.
Okay, cool.
Cool.
So this is. All right. Any takers?
I can try to explain number 4.
Awesome. Thanks, Lita.
Yeah, let me just join because I have my Mathematica on another computer. So give me
Sure.
a second. I'm gonna join. Okay, I think you can see my screen. So this was the problem statement that we had right here. You gave us some background on it. But basically just like right off the bat, you could tell, besides you tell us this was gonna be a boundary layer problem, we can also tell because the epsilon is multiplying the highest order term right here. So what I did was first I tried solving for my analytical solution and it worked. So I plotted it first just normal, and then I decided to do a log linear plot to just better visualize that right here. So this is kind of what we're aiming to match towards the end. I did a numerical solution, which didn't work, but it didn't matter either way because we already have our analytical solution. Just some definitions I set from the very beginning. So this is going to be our guess to do our expansions for our guess of the solution. And it's just defined like people have normally done it. Another thing I did was actually I added this extra variable right here. So that way I could like later on define it in terms of capital X instead of just little x. And that way I could like use it for both capital X and little x. So the first thing is you need to get your outer solution, which is going to be done through regular perturbation. And it's just going to follow the same process that everybody else has said so far. So you're just going to do your, you're going to replace your y or x with your expanded guess version. So that's what I'm doing right here. And then you do also the same for your boundary conditions. Then you only want to consider terms of order 1. So this is what this is doing right here. And then finally you solve for your unknown, which in this case is y naught of x. And I didn't solve for it like all the way because I want to see which boundary condition we needed to use. So I just solved for it like this, and then I plotted it with different values to see, to just kind of get a sense of like, okay, which boundary condition should I use? And these are original boundary conditions. So we want to see which one of these we will actually like cross with this. But as we can see, if we go to 0, 0, and then 1, 1, I think it's like somewhere over here. But like, you know, if you plot more discrete lines, eventually each line's going to cross, or not each line, you're going to have a line that crosses either 0, 0, or 1, 1. So basically either one of these boundary conditions works, and you can apply either one of them in this case. So I just went ahead and applied the second one, just because. And then you get your regular outer solution for order 1, which is this right here. And then you do the same process for order epsilon. So you just do some expansions, some simplification right there. You solve, and then you end up using, you also do your expansions again for your boundary conditions. And then you solve again, but you end up using your, you also use your second boundary condition again, because you had to use the same one that you used in order 1. And then to get your total solution, then you're gonna add up your solution that you got before plus epsilon, and then your solution of order epsilon. So this is just like how to get your full solution for order epsilon in this case. I just kind of wrote it out, but you can probably make this automatic if you want to. And then you plot this order epsilon solution, and you can see that it does end up giving you like a little bit of better match, but still not that full match as we can expect right here. So then we move out to find the inner solution, which is done through singular perturbation. So the first thing you need to do is do your change of variables, which is what I'm doing right here. So capital X equals X, little x over epsilon gamma. You just do your change of variables. You sub it back into your original equation to get your equation in terms of your change of variables. And then you do your method of dominant balance. I did this by hand because I just find it to be a lot quicker. So if anybody has any questions on that, I can answer it. But basically, after you just do all that, you get that gamma equals 1 is the best, it's like the version you're supposed to pick because that's what causes your highest order term to be dominant in the end. So you go ahead and just plug in gamma equals 1 into your equation, and you end up getting this. So and what you end up doing after you get your gamma is you do the same thing that you do the regular perturbation. So you just do the order 1, you plug in your estimated guess, you do some expansions with your equation, and then you end up solving, where is it? Oh, you also do the same thing for your boundary conditions. And then you end up solving down here. And the one thing to highlight is since we use the boundary condition, the first boundary condition in your regular the second boundary condition in your regular perturbation, you have to use the other boundary condition now. So we're using the first boundary condition to solve for this. And this is what we end up getting. But this is still in terms of big X. So we had to do a change of variables to solve it for terms of little x. And this is what we get actually in the end. This is just kind of what this looks like and plotted against your regular perturbation and your analytical solution. And you can tell that this is definitely not where we want it to be. So we need to go to a higher, oh, sorry. It is what we wanted. So it doesn't look like what we wanted to be at this point, but that's because we got to do limit matching, just kind of converge those two solutions. So we go ahead and do some limit matching right here. And so we're just finding the limit of your solutions for your regular perturbation, your single perturbation as they approach like the boundaries basically. and you're just setting those limits equal to each other because they're supposed to like meet to form like one single like composite solution. So you just find the limits and then you set them equal to each other, which is what I'm doing right here. So this is basically your limit matching solution that you get. And then what you have to do is you plug in this like limit matching, because this is like solving for C1. That's like your limit matching. You have to plug it back into your singular equation. So that way you, guess this one originally had like an unknown in it, and now you know what that is. So you plug that into here. And finally, to get your composite equation, it's going to be your regular perturbations, your outer solution, plus your singular perturbation, your inner solution, minus that limit matching, because you not only want to combine both of these, but you also want to subtract any overlap that they have. So that way you're like connecting them, but you're also not double counting any of the solution areas. And this is what you end up getting right here. So we plot this by itself. Again, I'm using log linear just because it's better visualization. And then you put it on top of your analytical solution. And you can see that's like a much better match than like the other ones over here.
So I'm gonna jump in right here. So one of the things that I think made this problem tricky is probably how I worded it in a way that was maybe confusing. It looks like everything you did for all your steps was correct. The confusing part that I worded that probably added some complications was this discussion around taking a value for A and setting it to 1. And what I wanted to do but did not make clear was to have you kind of do the solution for some arbitrary value of A, and then after you kind of analyze the boundary layer, inner and outer kind of composite solution, to see how the problem changes once you set A equal to exactly 1. So this problem, so kind of, I guess, spoiler alert, the boundary layer disappears when A is equal to 1. And so your math is correct, but the kind of the singular nature of this problem goes away at this particular value of A. And this is a kind of one of the first examples we see of kind of like a qualitative change in the solutions to your problems as you play with one of the parameters, which we'll talk about a little bit more in a few weeks regarding bifurcations and instabilities in solutions as the qualitative nature of your solution changes. Out of curiosity, did anyone who's willing to share solve this problem kind of for an arbitrary value of A that was not equal to 1, so we could see how the boundary layer kind of appears and changes as A changes?
I have some graphs I could show.
That would be super helpful. Who said that?
Susan. I should already be able to screen share.
Okay, awesome.
Cool. So I guess this one that I'm showing first is the new analytical solution. So I think I took A to be like a bunch of numbers from like 0.1 to 2 or something. And then this linear line here is A equals 1. Yeah. And
yeah, this is perfect. Thank you, Susan. Yeah.
Yeah, and then so as you go to the regular solution, you kind of see, so the dotted red lines are the regular perturbation, and so like at A equals 1 it is exactly, but then the other ones are not, and so.
And this is important because at A equals 1, as Alita said, you could choose any boundary condition. You can actually match either one perfectly fine, but when A is not equal to 1, you're unable to do that because those values of Y kind of have to force through the origin, and you see the appearance and the width of this boundary layer. I don't know if you can see me, but like the boundary layer is occurring in here, from between x is equal to 0 and x is equal to, say, 0.2. And then the boundary layer disappears once a is equal to 1. And then as a, I think, either decreases, it appears again, but it has a different kind of qualitative form to it. So part of what so what Alita presented is correct. And my wording of the problem, I think, made it a less rich problem than it could have been, because what I wanted to get across was there's this boundary layer in this viscous fluid flow problem that, as we've set it up here, that boundary layer disappears for a specific value of that unknown parameter a, and that represents kind of a qualitative change in the problem, as a problem that has an inner and outer solution to a problem that doesn't, to a problem that is actually a lot simpler. And so this is my fault. And so I think I just want to emphasize that kind of this is the first problem in which we've seen where there's a boundary layer we need to consider. It's a singular perturbation problem. We're matching inner and outer solutions, and yet there's an additional term in the parameter that can qualitatively change the behavior of our solutions. And in this case, qualitatively change it in a way that it removes the main feature that we've been studying, which is the appearance of a boundary layer. And so, yeah, I just wanted to throw this out there. This was my fault. I didn't do a particularly good job of wording this problem. I think it added some ambiguity along the way. So, what questions do people have about this?
How did the limit of the regular perturbation solution come out to, what was it, 1 minus a minus 1 or something?
So the question was, how did the limit of the regular perturbation come out to 1?
What was the expression you found for the regular perturbation? Or just the regular perturbation, first of all?
Susan, would you mind showing what you had for the regular? It's right here, right? It's 1 minus a plus ax.
So yeah, the solution for the first order was
And then you take the limit as x goes to 0, because x is the outer solution is away from the origin. You take the limit as x goes to 0, it becomes the 1 minus a.
For some reason, I was finding it as C1. So that's why I'm asking what their, I guess in this case, Sol order 1, 4.
Sol order 1, 4.
What's the expression inside that you're taking the limit of?
I think the Sol order 1, 4 is that one. Yeah, 1 minus a plus ax. So as x goes to 0, that becomes 1 minus a. Well, you can just see it, right?
I had a problem where my solution, well, what the variable is in this is solution order 1, 4. Mine was a minus a plus ax, not 1 minus a plus ax. And I'm pretty sure like I did the same, like use the same logic. And I think my Mathematica has been just computing things a bit weirdly.
I think if you use the other boundary condition, you end up with a, or like negative a plus ax or whatever it was. Like if you flip where you use your boundary conditions.
Yeah, that's correct. So can you scroll up to show which boundary condition you used for this? I think you used the one away from it.
So I used, yeah, I said this, yeah, I used y1 equals 1.
Yeah, if you use the other boundary condition, as Susan just said, you'll get the result where the 1 basically goes away.
I used y0 equals, I used y1 equals 1. I used the same boundary condition, but I got a different answer, which I'm not sure why.
That's surprising. Okay. Well, I'll have to take a look at your notebook to see why that happened, but
I can send it to you. I mean, I can like discuss it with you in office hours or something.
okay. Yeah, absolutely. Reese, question?
Yeah, I had a question. So, I guess it's mainly like a conceptual thing, but essentially it was brought up earlier that, there was the first plot, and I think they were varying the values of A. It was like where it's all y equals x at different values.
Yeah.
And then the conclusion was that like you can use either boundary condition.
Only if A is equal to 1.
Only when A is equal to 1.
Only when A is equal to 1. And that's where this problem becomes confusing. When A is equal to 1, you get that straight line that runs through the origin and can be found a slope so that it runs through y at 1 equals 1. But if any other value of A, then that inner boundary condition can't be met with for the outer solution. You'll find that it'll intercept at a value that's not 0 when A is a different value, and you kind of need to force it through the origin. And so that's the.
I guess the motivation for my question is sort of like becoming better at identifying where the boundary layers are. So is it mainly just like it should be obvious from those plots that it can meet one boundary condition, or you can get a solution at one end but not the other, like we had seen before?
Yeah, Susan, would you mind showing the graph you had again with all the different A values? I can maybe talk through this a little bit.
Yeah, sorry.
Thanks.
Just is that good, or do you want?
Yeah, no, that's perfect. So just the first question that Reese was asking is like how to identify where the boundary layer is. And the way I typically do that, if you have a problem that you can solve numerically, for instance, to identify where the boundary layer is, solve it numerically for like 3 or 4 different values of epsilon. And you're going to look to see how that kind of qualitatively changes the curve. And what you would find in a case like this is that so take the top curve on this graph. As you change epsilon, what you're going to find is that the slope of the top curve between x is equal to 0 and x is equal to like 0.25, the slope in that region is going to change. As you decrease epsilon, that curve is going to become steeper and steeper and steeper. That's your boundary layer. Is the kind of like the qualitatively near this boundary, and particularly near the boundary of x is equal to 0, my solution is changing rapidly as epsilon gets smaller. And remember, that's kind of how everything is. It's kind of central to everything we're talking about, is that as x gets smaller, something is happening to one of the terms in your differential equation that will eventually lead it to go away. And that is going to kind of happen at one or more locations in your curve. And changing epsilon is the quickest way. If you can do that, if you can change it numerically and solve for it, you can really quickly see like, oh, okay, as I make epsilon smaller, this is the region of the curve that's qualitatively changing. That's the region where your boundary layer is. And that's the region where I need to rescale my axis around x is equal to 0. My outer solution will be away from that. In this case, the domain is from 0 to 1, so my outer solution is going to be around x is equal to 1. That's the way I would approach trying to find my boundary layer. So if it's not obvious to you where it is, take the solution, fix the value of A here, and then just plot it for different values of epsilon, where epsilon is getting smaller, and watch how that curve is changing, and that'll tell you where that boundary layer is. I hope that kind of helps. Yeah. All right, this was really good. Thanks, Alita. Thanks, Susan. Hopefully that clarified some stuff. And I guess we just have one more problem.
Oh, can I ask a quick question about number 4?
Sure.
So I changed the epsilon from like really small number to 1. But when the epsilon becomes 1, one side of the boundary doesn't match with the exact solution. So I'd like to know what was causing this, because epsilon was not small. Because since all of the stuff we've done was fixing the solutions, two solutions for two boundary conditions. So what I was expecting when I increased epsilon was maybe it does not have a very good approximation on the middle part, but it should have a nice matching on the boundary.
That's what I would expect too. And so I don't know why that's the case, I guess, without digging into your code. It should match your boundary conditions, and it should start to deviate away from the boundary conditions. And so my intuition is the same as yours. And so maybe I can take a look at your work and chat with you about trying to see what's happening there, because I would have thought the same as you.
Yep, that'd be great. Yeah.
Excellent. So we can maybe talk talk about this in like office hours or over email or something. But that's a good question. I don't know if other people can, if their solution is easy to play with, can try to see if they see the same thing. I think you should find that it should match the boundary conditions and deviate in the middle, but we should confirm that.
Yep, thanks.
All right, does anyone want to do number 5?
I can do number 5.
Awesome.
This is Carolyn, by the way.
Cool, thank you. What? That's not what I want to do. What? There we go.
Okay, you guys should be able to see it now.
Excellent.
So the beginning, just setting up the problem with your equation and your two boundary conditions. You can solve this analytically. It gives you really nasty result, but if you plot it, it looks something like this. So you kind of know that you're going to have an inner and an outer solution, also just based on where your epsilon is, which is on your highest derivative term. So then going on to the outer solution first, for order 1, I assumed that your y value is, this y naught of x plus y1 of x. And then for the first order, it would just be y naught of x. So substitute that in to your equation and boundary conditions, and then trim it for just order 1. So taking epsilon to 0, and you're left with this for your equation. Your boundary conditions are already at order 1 based on how I plugged it all in. And then you can solve it, and when you plot it with your analytical solution, you get something that's pretty good at one end of your x boundary, but then it starts to deviate as you get closer to where your inner solution would be. So I took it out to order epsilon, which I won't really go through since we've done it a bunch of times at this point, but you basically just keep your y1 term, solve for y1, and when you do that, you have a curve that matches your outer solution for a longer kind of span of x. And then moving to your inner solution, and I guess I kind of forgot to mention, when I was solving all of these, I was using your second boundary condition right here. So y1 is 1 is the boundary condition I was using. And now going to the inner solution, doing the change of variables to set up the singular perturbation. We've kind of done this a bunch of times as well, so I won't go too in depth with it, but changing your little x to a capital X and your little y to a capital Y. And then you can do that variable change on your equation, but also your boundary condition. I was a bit lazy and only did it on the first boundary condition because I know that's the one I will be using because I already used my second boundary condition. And then you can do your dominant balance to find your gamma. And when you do that, you find that gamma should equal 2 so that your second order derivative doesn't get lost when epsilon goes to 0. And then you can do your order 1, which again, just replacing your y of x with y naught of x, which is your guess for order 1, and doing the same thing for your boundary condition. You can rearrange and then take only order 1 term, so making epsilon go to 0. And then when you do that, you find that your inner solution, y naught of x, is equal to this function right here. And to find your C1, we're going to do that matching that we've done in a couple other problems. So matching your outer solution as x goes to 0 with your inner solution as big X goes to infinity. And then you can set those equal to each other, find what your C is, and put that back into your big Y naught of big X. And then you can sub back in your little x. You get this really fun equation here. And then you make your composite solution by taking
Oh no. Uh-oh.
in some of our other problems, C1 or that constant was just your inner solution, just based on how the limits worked out. But here it's 1 plus C1 is your common part. And then when you plot that all together, you get this curve, which matches really well, obviously, at your boundary conditions, but not so great kind of in this region where it dips down. I did try to do my inner solution to order epsilon, and I won't go through all the steps, but I did have a question on it. Basically, I found what a y1 of x would equal. And then when I tried to do my matching, it basically told me that my y1 was 0 because C1 came out to be 0, so this whole term went away. And so I was kind of wondering if I did something wrong with my matching, and if it's kind of like the situation with the boundary conditions where we already used this matching condition to match our first order inner with our outer solution. So since we match those two, is the only way for that previous matching condition to be met for y1 to be 0, kind of like how the boundary condition will change as you go to higher order epsilons. So that was just one question I had about this problem, was if you wanted to take your inner solution up to higher orders, how you would do that.
So first off, thank you. That was really clear and it looked really nice, and I think the solution looks great. Second, to get to your question, I think what you could try is to, if you're going to take your inner solution to, so maybe you did this, and so maybe I'm misunderstanding, but I think what you can try is to kind of take your outer solution to whatever order you want, take your inner solution to whatever order you want, and at that point, then do your matching. Instead, I don't think you would typically match along the way, because I think what ends up happening is you do kind of cancel things out. And so my sense is, and maybe you tried this, and so maybe what I'm about to say is already a moot point, but my sense is if you just didn't try to match them at order 1, and you only tried to match them at order epsilon, would you be kind of left with an appropriate matching condition where everything just doesn't drop out and go to 0? So I don't know, maybe you can, does what I'm saying make sense?
Yeah, that makes sense. I didn't try it because I was, I guess, didn't exactly know how you would solve for all your constants, because then you would have 2 constants, but only like 1 expression to solve for it. And I guess maybe that's where the boundary condition comes in. So I guess I just wasn't entirely sure like the order of operation to find 2 constants, because you would have to leave one of your C1s, like you would have to leave your C in there for your like order 1.
Yeah, that's a good point. I think, yeah, I have to think about that. My experience with this has always been kind of trying to take them to whatever order I want to stop the perturbation at, and then doing the matching as my last step. And so it doesn't answer your question, which is a good one about, well, what happens to the extra constant. I have a sense that if you apply the boundary condition at that order, you at least get rid of one of them. So yeah, I have to think about that. But the thing I would try would be to seeing if you kind of hold off on matching until later and see what see if that works out for you. So maybe we can try that.
Professor,
Yeah.
I got the same question. So I have two constant. I have only one equation to solve the constant. So yeah, so when I did it, so it's something that went wrong, and I can't get the two constant.
Okay. Well, then I guess I'll try to resolve this and maybe post the solution to this one, so that way we can get a better match up to order epsilon for these ones. And so I don't know offhand what would fix it quickly, but I will try to resolve this and post the solution somewhere.
And after looking at it a little bit more, I kind of wanted to just try taking it out to order epsilon, just so I had my inner and outer to the same order. But if you look at the graph, where the discrepancy is kind of more on the outer solution. So I'm not even sure if taking your inner solution to the next order really helps you. I think if you took your outer solution to epsilon squared, you would probably eliminate this gap a little bit more. But it was kind of just out of curiosity. And then when I was running into the problems, I just had more questions.
Yeah,
So,
no, that's a good point.
Yeah.
Yeah, so I'll try to see if I can resolve this, but these are good questions about kind of what's happening to that apparent extra boundary condition. I think we can resolve it. I'm pretty confident, but I'm hesitant to try and do it right now, but I think we can sort this out. I'll try to post the solution once I figure that out.
Okay, thank you.
Thanks, Carolyn. And thanks everyone. If there's no more questions, I think we hit everything. I'm gonna send out the midterm take-home project-y thing. It's basically like a bigger homework assignment, one problem that is kind of multifaceted, and I think it'll help tie the first half of the semester all into one kind of neat little package. So I'll send that out soon with some instructions. But otherwise, yeah, have a good week. I'll see you all a week from today, and hopefully we'll be on a better path for our country. See you all.
Professor, when is the midterm due?
I will send out, I usually give like 2 weeks for the midterm, longer than a normal homework assignment. So it'll probably be due in a couple of weeks, like say like the middle of November or something.
Are we expecting no classes during the midterm then?
No, there'll still be classes. It's just like a take home. It's like a long homework assignment essentially.
Okay.
That is a little bit. I don't necessarily know if it's not even necessarily super hard. It just kind of allows you to go through like formulating a model, non-dimensionalizing the model, finding epsilon, approximating your solution, doing the matched bound, all of the steps that we've done, but for one problem, which is a lot more of how you would experience this in a research setting. And so it's mostly just a chance for you to tie it all together. But yeah, there'll be classes, just no class on Tuesday, but I'll be on that. There's regular classes.
Yeah, thanks.
Mm-hmm.
Will you have office hours next week since we don't have class Tuesday?
Yeah, good question. Yeah, I think I will plan on, if people are interested in meeting with me on Tuesday afternoon in like where I normally have office hours, just send me an email early next week so I know to be on. And if I don't hear from anyone, I will not. And if I do, then I'll jump on and have office hours.
Okay, cool. Thanks.